On July 23, 2026, off the coast of Odisha, a new interceptor missile tore through the atmosphere to destroy a high-altitude target. That successful interception marked the exact moment India's sovereign long-range surface-to-air missile program, known as Project Kusha, moved from theoretical architecture into flight-proven hardware. Media coverage quickly reduced this milestone to a lazy shorthand, calling the new system India's S-400. While Kusha matches the 400-kilometer range of the Russian system, labeling it a clone ignores the technical reality. This is an indigenous architecture, engineered with specialized seekers and command software to address modern threats the S-400 was never designed for. Defense scientists engineered a highly modular, AI-driven kinetic backbone for mission Sudarshan Chakra, a layered defensive dome optimized for modern aerodynamic and intermediate ballistic threats. To understand how it actually works, we need to deconstruct Kusha's architecture chronologically, tracking a theoretical interception from the first radar ping to the terminal kinetic impact. This marks the evolution from buying isolated point defense batteries to engineering a unified, sovereign network of airspace denial. Before launch, threats must be found. This process is governed by the Integrated Air Command and Control System, or IAACCS. Instead of relying on a single radar, AI fuses data from civilian and military platforms into a single situational awareness grid. This enables cross-system targeting. If an external radar detects a threat, IAACCS instantly routes the coordinates to a Kusha battery, allowing it to fire an interceptor blindly based entirely on that feed. During a saturation attack, such as a drone swarm, human latency is a fatal flaw. The AI minimizes this delay by automatically prioritizing threats and actively guiding Kusha's missiles toward at least 10 different targets simultaneously. But Kusha also brings its own highly advanced organic detection to this network, gallium nitride-based active electronically scanned array radars. Unlike older mechanical radars, this AESA system relies on thousands of individual transmitter and receiver modules operating simultaneously to generate a 360-degree tracking volume. Because it uses gallium nitride, these modules handle vastly higher power levels, burning straight through severe enemy electronic warfare. This concentrated power is specifically designed to negate the low observable geometries and radar-absorbent materials used by modern stealth fighters. By fusing the IACCS network with GaN AESA radar, the system strips the adversary of their primary advantages, stealth and electronic blindness, long before an interceptor even leaves the launch tube. Once the network isolates and assigns a target, the battery must immediately select the appropriate interceptor to match the distance and speed of the threat. Project Kusha is built around a modular assembly strategy. Instead of developing 3 distinct missiles, every variant shares the exact same standardized hit-to-kill vehicle. For drones at 150 kilometers, the system attaches the smallest M1 solid rocket booster. For tactical targets further out, the larger M2 booster extends the envelope to 250 kilometers. To reach extreme distances of 400 kilometers, the massive M3 booster provides enough thrust to propel that same core vehicle up to Mach 5.5. This M3 variant is strictly reserved for hunting high-value strategic assets, like AWACS command planes and mid-air refuelers, as well as intercepting hypersonic glide vehicles. Building one universal kill vehicle across 3 distinct missile ranges drastically simplifies the manufacturing supply chain for state-owned defense contractors like Bell and BDL. This modularity yields a significant economic advantage. A single Kusha interceptor costs roughly $6 million, about half the price of a comparable S-400 interceptor. That brings the cost of a full Kusha squadron down to $600 million, compared to nearly $1 billion for an imported equivalent. Modularity transforms defense procurement from building bespoke, expensive batteries into mass-producing a highly scalable arsenal. Regardless of which booster gets the kill vehicle to the target area, the final seconds of the interception, the terminal guidance phase, are the most complex part of the kill chain. At these extremely close ranges, advanced stealth shaping and intense electronic jamming can completely blind standard radio frequency seekers. Kusha utilizes a dual seeker architecture. The interceptor's nose houses an active radio frequency seeker and an imaging infrared camera. If radio waves fail to return off stealth geometry or the signal is jammed, the IR camera takes over, locking onto intense, unavoidable engine heat. To pursue highly maneuverable targets at Mach 5, the missile executes rapid micro-adjustments using thrust vector control. Flexible blades redirect the rocket plume in microseconds. These terminal corrections must be perfectly precise because Kusha relies on hit-to-kill technology. Instead of detonating a traditional explosive warhead near the target, the interceptor relies on the kinetic energy of a direct physical collision. When intercepting an advanced threat, like a hypersonic vehicle, the combined speed of the two objects ramming into each other results in physical obliteration. However, if an evasive maneuver causes the physical collision to narrowly miss, the interceptor features a backup optical proximity fuse that detects the target's distance and detonates a secondary explosive blast. The combination of dual seekers and kinetic impact ensures that even if an adversary breaks a radar lock, they cannot outmaneuver the missile and they cannot hide their thermal signature from destruction. To understand the complete architecture of India's defense, we also have to clarify a strategic boundary: what Project Kusha is explicitly not designed to do. This graph outlines India's airspace. Kusha's operational dome is limited to the endo-atmosphere, capping at a 400-kilometer radius. It does not cover the exo-atmosphere. That edge of space domain belongs to the entirely separate Indian Ballistic Missile Defense Program, utilizing PAD and AAD interceptors. Stopping intercontinental ballistic missiles diving from space requires completely different interception logic and hardware. That is the BMD's exclusive domain. Instead, Kusha occupies a specific middle layer. It bridges the gap between 80-kilometer short-range systems like the Barak 8 and the outermost BMD shield. By defining Kusha as a middle to outer atmospheric shield against aerodynamic and intermediate threats, military planners prevent strategic overlap and maximize the efficiency of the overall network. Following the successful validation of the M1 variant, developmental trials for the longer-range M2 and M3 interceptors are scheduled to run between 2026 and 2028. The Ministry of Defense has set a firm target to achieve full operational deployment of the first 5 Kusha squadrons between 2028 and 2030. While Kusha is initially being integrated to complement existing S-400 batteries, its ultimate engineered purpose is the total replacement of those foreign-supplied systems. This serves as a critical geopolitical safeguard. Owning the source code, the advanced sensors, and domestic manufacturing lines protects the Indian military against supply chain disruptions and the threat of foreign sanctions. Ultimately, Project Kusha guarantees India's strategic autonomy. It completes the transition from being a reliant buyer of imported point defenses to becoming the chief architect of its own sovereign airspace denial. Following the successful validation of the M1 variant, developmental trials for the longer-range M2 and M3 interceptors are scheduled to run between 2026 and 2028. The Ministry of Defense has set a firm target to achieve full operational deployment of the first 5 Kusha squadrons between 2028 and 2030. While Kusha is initially being integrated to complement existing S-400 batteries, its ultimate engineered purpose is the total replacement of those foreign-supplied systems. This serves as a critical geopolitical safeguard. Owning the source code, the advanced sensors, and the domestic manufacturing lines for the kill vehicles protects the Indian military against supply chain disruptions and the threat of foreign sanctions. Project Kusha guarantees India's strategic autonomy. It completes the transition from being a reliant buyer of imported point defenses to becoming the chief architect of its own sovereign airspace denial.